Question 1 should be quite straightforward. It tells you the mass of the ball and it tells you the speed that it's thrown with. In other words, that's how fast it's travelling when it leaves your hand. The first thing it asks is its kinetic energy when it's got that speed. So if you know anything at all about kinetic energy, you know the formula for it. You've got the mass, you've got the speed, you can find the energy. Part B, its maximum gain of potential energy. Well, as long as we remember that as it's travelling upwards, it's losing kinetic energy and gaining potential energy, and it will have to stop gaining potential energy when it's lost all its kinetic energy. So that should help you to very quickly work out what the maximum gain of potential energy will be. And for part C, its maximum height gain. In other words, how high does it travel when you throw it? Well, if you know how much potential energy it gains, and you know the formula for potential energy, you should be able to work out how high it's risen. In doing question 1, we've actually assumed that no energy is ever lost due to friction or air resistance. And it's reasonable to assume that because the ball's never travelling very fast and it doesn't travel very far. The situation is going to be different in some of the other questions that follow. In question 2, the ball starts 1.5 metres above the table. So it starts with potential energy, and as it falls, it's losing potential energy and gaining kinetic energy. So the first part of the question calculates how much potential energy it loses as it falls. Well, you know its mass, you know how far it's going to fall, you know how strong the Earth's gravitational field is, so you're able to work out the loss of potential energy. For part B, after it's bounced, it rises up again above the table, and it tells you how far it rises, so you're able to work out how much potential energy it gains on the way back up. Part C, to find how much energy is lost due to the impact. Well, after it's rebounded, it doesn't finish up as high as it started. It starts from 1.5 metres and it only gets back to 1.2 metres above the table. So the amount of energy associated with that must have been lost on the impact. So if you work out the difference in potential energy before you drop it and after it's rebounded, that's the energy lost due to impact. Question 3 is about a cyclist freewheeling down a hill, and it's important it tells it's freewheeling because that means that the cyclist isn't pedalling, so they're not putting any energy in themselves. So all the energy that's going to be involved in this question is going to be coming from potential energy. So the first thing we've got to find, part A, how much potential energy does it lose? Well, there's quite a lot of words in there, but we can work out from the words what the difference in height is. So if we know that, we're able to work out the potential energy change. Now in this case, because there is friction present, the potential energy lost will be greater than the kinetic energy gained. So part B, calculate the gain of kinetic energy for the cyclist in the cycle. We've got to use the information that's given about the speed. So we'll work out the kinetic energy using the formula that involves mass and speed. Part C, the work done against friction and air resistance. So hopefully, when you look at the answer to A and B, the answer to A should be bigger than the answer to B. And the reason is that works had to be done against friction and air resistance. So if you take the difference between the two answers, for A and B, that should be the work done against friction and air resistance. For part D, once you know how much work was done against friction and air resistance, you just need to remember the formula for work done that involves force and distance. So you've got the work done, it tells you the distance it's travelled, it's 500 metres down the hill. So you know the work done, you know the distance travelled, you should be able to find the force, which in this case is the resistance force. Question 4 uses similar ideas to question 3, but it's slightly more complicated. Because one of the things is that the car is moving at the start, whereas the cyclist started from rest. So if we look at the different parts of the question, part A, you've got to calculate the loss of potential energy. Well, we know the mass, and we're told the height through which it descends, so that's the delta H. So it's easy to find the loss of potential energy. Part B, we're asked to find the initial kinetic energy. Well, we do know the mass, and we know the speed at the start, so we should be able to work out the kinetic energy at the start. For part C, what's its kinetic energy after the descent, once it's gone down the slope? So the mass will be the same, and it tells you the speed it's going to be travelling after the descent. So it should be easy enough to work out the kinetic energy. Part D, just like with the previous question, we should find that the gain in kinetic energy is less than the loss in potential energy. Remember, we're looking at the gain in kinetic energy, so we've got to think about the kinetic energy at the end and take away the energy at the beginning to find out how much energy it gained. And you should find that the gain in kinetic energy is less than the loss in potential energy, because some work's been done against friction. So whatever the difference is, between the potential energy lost and the kinetic energy gain, that difference will be the work done against friction. And once you know the work done against friction, you know that work is force times distance. And the question tells you the distance that the car travels. So if you know the work that was done and you know the distance, you should be able to calculate the force that the work was done against, which in this case is the frictional force.